Hey everybody, Dr. White back again with my barking dog Demi down by my side, so pay no attention to him. And we're getting into section 1.3 on conditional probability. Hope you enjoyed section 1.2 on methods of enumeration, and I hope you kind of see how useful it can be in probability, because so often probability situations, we're going to be using that equal likelihood principle, where the probability of an event is the number of things that make up the event divided by the number of things in the sample space because of the equal likelihood. And the enumeration lets you count how many things are in that event. Super useful stuff. But in this section, we'll keep that stuff in mind, but we'll kind of press on and refine some of our notions of probability. Going to bring up the topic of conditional probability in this section. So start off with an example. Say you got a group of 20 people, some are male, some are female, and you ask them a question about like whether or not they own a pink sweater, and everybody answers that question yes or no. And let's say what you find out is that of the 12 females in the group, 8 of them own a pink sweater and 4 of them do not. And there's 8 males in that group of 20, and say that one of them owns a pink sweater and 7 of them do not. Okay. Now I've written some totals down here. 9 people in the group own a pink sweater and 11 do not. Again, that adds up to our grand total of 20. Now say that we decide we're going to select a person at random. That's our little random experiment here. And so there's all kinds of like outcomes. I guess each an outcome is like, a person, so there'd be 20 outcomes. And there's events, and we can ask about their probabilities. So how about the event that the person that you pick owns a pink sweater, OPS? What's the probability of that? No problem with the equal likelihood principle. Then you say, well, it's the number of items in the event owns a pink sweater, that's 9, divided by the size of the sample space, 20, 9 over 20. So a little under 50% chance. But what if somebody randomly picks the person for you, and they will not reveal the person to you, but they will reveal that the person they have picked is a female, okay? Does that change your estimate of the chances that the person owns a pink sweater? Surely it should, because there's these 12 females, right? And you know that of the 12, 8 of them own a pink sweater. Now, the person was randomly picked, so presumably any one of those 12 females was equally likely to be the female that, they said they picked. And so that same equal likelihood principle would say, well, 8 ways for the event to happen now, 12 ways to get a female, 8 over 12, okay? What you've just done is a conditional probability, and the way we write it is like this. The probability of the event owns a pink sweater given, and then there's that vertical line, the event that the person is a female. Okay, so that's conditional probabilities, the way we write them. Now, what you should notice mathematically is that 8 over 12 could be written as 8 over 20 divided by 12 over 20, which seems like a stupid thing to do until you realize that 8 over 20 is the probability of the event the person owns a pink sweater and is female. And the 12 over 20 is the probability of the event person is female. So you can reframe your computation where you kind of like narrow down on the females. You can reframe that computation as the ratio of 2 probabilities. And that leads to an actual mathematical definition of conditional probability. The probability that event A occurs given that the event B definitely occurs is the probability of A intersect B divided by the probability of B. So that like division there is that way that you narrow down on the a smaller group given your knowledge about the event B. I should point out that conditional probability satisfied basically all of the standard probability laws that you've been learning about and proving lately. For example, the probability of A given B is always at least 0. And that's because it's this ratio here. And, well, they're probabilities, and probabilities are always at least 0, so the ratio is at least 0. It's also always going to be less than or equal to 1. And the reason is that the top of that fraction, the probability that A intersect B, has got to be less than or equal to the probability on the bottom of the fraction, the probability of B. Why is that? Think about that for a minute. Okay, and I bet you thought about it. It's the fact A intersect B is actually a subset of B. And so one of the laws of probability says that its probability has to be less than or equal to the probability of B. Here's another one, just to kind of show you. Say that A1 and A2 are disjoint events. What's the probability that either A1 or A2 happens given that B happens? Turns out it's the probability that A1 happens given that B happens plus the probability that A2 happens given that B happens. So that sum rule that you know about probability applies to conditional probabilities as well. Why does it apply? Well, let's give it a try. Probability of A1 union A1 union A2 given B, by definition, is the probability of A1 union A2 intersect B divided by probability of B. And to this little intersection here, we can apply the De Morgan's law of set theory and rewrite that as A1 intersect B union A2 intersect B. You can, again, if you're not liking to use formal laws, you can still think of it intuitively. To be in A1 or A2 and also to be in B, well, one way to do that is you could be in A1 and in B, or you could be in A2 and in B. So that's the same set, so it's got the same probability. And so this ratio is the same as before. Now, the fact is that A1 and A2 are disjoint, so A1 intersect B can't have anything in common with A2 intersect B because A1 and A2 can't have anything in common. So by the definition of probability, that third part of it, the probability of that union is the sum of those probabilities. And then you can break that fraction up into two of them here. And each one of them, by the definition of conditional probability, comes down to this. And you're done. If you take the definition of conditional probability and you play with it algebraically just a tiny bit, you get a really neat principle of probability that is called the multiplication rule. It has some underlying resemblance to the multiplication rule for the subject of enumeration, but it is a rule of probability as we're stating it here. So here's the idea. Since the probability of A given B is defined like this, multiply both sides by the probability of B, and you get this. The probability that A and B both happen is the probability that B happens times the probability that A happens given that B happens. Now, of course, this is only going to make sense when the probability of B is not 0. You don't want a 0 in the bottom of a fraction. Now, the definition of the probability of B given A would be the probability of B intersect A divided by the probability of A, right? And so you could multiply both sides of that by the probability of A. Getting probability of B intersect A is probability of A times probability of B given A. Sorry, missing closing parentheses there. Now, the B intersect A is the same as A intersect B. So another way of finding the probability that A and B happen is to find the chance that A happens and multiply by the chance that B happens given that A happens. So you can do either way to find the probability of an AND. Again, this only makes sense when the probability of A is 0. Okay. So let's apply these ideas of conditional probabilities to new problems. We got exercise 5 out of section 1.3. So what's 5 up to? Says, suppose that the gene for eye color for a certain male fruit fly has alleles R for red and W for white. And the gene for eye color for the mating female fruit fly also has alleles R and W. And their offspring receives one allele for eye color from each parent. So you get an R or a W from your mom, and you get an R or a W from your dad. And those alleles are going to determine your eye color. Part A just says, like, what's the sample space for, like, what your alleles could be? And so you could use some lettering, and you could write out sample space maybe like this, RR. And so like the first R is like the allele you got from your mom. And the second R is the allele you got from your dad, maybe. And then keeping that convention, here's where your mom gave you an R and your dad gave you a W. Or your mom gave you a W or your dad gave you an R, or they both gave you a W. And that seems to be all the possibilities. That's our sample space. Great. Okay, part B. Assume that each of the 4 possible outcomes has equal probability. Okay. If an offspring ends up with either 2 red alleles or 1 red and 1 white allele, its eyes are going to look red. And so the red allele is what they call dominant in genetics. All right, now here's the question. Given that an offspring's eyes look red, what's the conditional probability that it has 2 red alleles? So we're asking for the probability that the offspring is a red-red, given that it looks red. Now, the event that it looks red comes down to the event that it either has RR or has RW or has WR for its alleles. And so this conditional probability, by the definition, is going to be the probability of the RR intersect the thing you're conditioning on over the probability of what you're conditioning on. It's the definition of conditional probability. Now, if you stare at this complicated set here, then you realize that it just is the same as the set RR. You know, to get in that intersection, I got to be an RR. I also got to be an RR or other stuff, but that just comes down to being the same as got to be an RR. So the top set's actually pretty simple. So I'll rewrite it like that. Now, as far as that bottom OR, that's an OR of exclusive events, mutually exclusive events. You can't have an RR and an RW, for example. And so by the part 3 of law of probability, I get to sum those 3 probabilities you see on the bottom there. Now, all of the 4 outcomes were equally likely, so each of them had a 1 in 4 chance of occurring. So I write that in here. And I get a 1/4 over a 3/4, which simplifies to a 1/3. Intuitively, a lot of people might have thought the answer was a half, you know, because they think, well, if your eyes look red, you got an RR, or you got a 1 red and 1 white. And they kind of forget that there's 2 ways to get the 1 red and the 1 white. But doing the computation makes it more clear. Let's take a look at exercise 7. Okay, an urn contains 4 colored balls, 2 orange and 2 blue. So here is a picture of the urn, okay, with an orange and a blue and a blue in it. Okay, 2 balls are selected at random without replacement, and you are told that at least one of them is orange. What's the probability that both are orange? And a lot of people would say something like 1/2. They just like leap at an answer. And that's, you know, because there's like 2 oranges and 2 blues, and you know, there seems to be a kind of a halfness symmetry to it. And that just shows your probability really needs to go beyond your, you know, straight up common sense. You got to try the definitions and the laws. So what's the probability that they're both orange, given that you're told that at least one of them is orange? So by definition of conditional probability, well, actually, let's rewrite first of all, the event that at least one of them is orange. And so that's the event that your draws were orange and then orange, orange and then blue, blue and then orange. And so the conditional probability is the probability of the A intersect the B over the probability of the B, okay? And when you look at that intersection there, you realize it simplifies down, like the last example, to just orange, orange. And now let's start thinking about each probability. What's the probability of orange, orange, okay? I say that it's 2 over 4 times 1 over 3, but how am I getting that? Well, the probability of orange, orange is the probability of what orange, orange means. The first one was orange, and then the second one you picked was orange. That's the probability of an intersection. Let's use the multiplication rule from this section. Probability that the first one is orange times the probability that the second one was orange, given that the first one was orange. Multiplication rule. Well, when you're taking your first ball out of the urn, there's 4 balls there. You're picking at random, and 2 of them are orange. So equal likelihood rule says 2 out of 4 should be your chance that the first one is orange. There's that 1/2. But then how about that? How about the next probability? Well, given that the first one was orange, and you're picking without replacement, that orange did not go back into the urn to be picked again. There's only going to be 3 left. And out of those 3, there's no longer 2 oranges, there's only 1 orange. So 2/4 times 1/3. That's how I'm getting this probability up here for orange, orange. And in a similar way on the bottom, so here's the probability of orange, orange again. Probability of orange black, orange blue, is the probability of orange, 2 over 4, times the probability of blue, given that you pulled out one of the oranges. There's still 2 blues, 2 over 3. And the probability of blue-orange works out to be the same thing for symmetric reasons. So you can multiply the top and the bottom of this fraction by 12 and get this, and then you can just compute stuff, and it turns out to be 2 over 10, which is 1/5. And like, I never would have thought that coming into the problem. The answer is 1/5. You gotta do the computations with the definitions and known laws in your algebra. This is sort of number 9, okay? So before I read any problems about this, I'll tell you what I'm doing here is I'm going to reach for a formula for the probability of the OR of 4 events. The probability of the A1 union A2 union A3 union A4 in any old situation at all where A1 and A4, A1, A2, A3, A4 are just 4 events. And from the previous section, when you do the homework, you actually prove the formula for the probability of the union of 3 events. And my idea is to be lazy and to use that formula, okay? In addition, we also know that the probability of the union of 2 events, we know a formula for that one too. Now I'm going to be lazy and use that formula. So how do I start myself off? What I do is I'm grouping the union of A1, union A2, A3 together as one set, and think of that as being union with A4. So I've got the probability of the union of 2 sets, which is the probability of the first set plus the probability of the second set, I should say event, minus the probability of the intersection of those events, okay? And then I got the same stuff here, but I'm just going to apply a little De Morgan's law to this intersection here to get that set is A1 intersect A4, A1 intersect A2 intersect A4, A3 intersect A4. Alrighty. And then I'm going to go ahead and use my formula for the union of 3 events. So it's the sum of the individual probabilities minus the various ways of intersecting, the three ways of intersecting two of them at once, plus the only way there is of intersecting all three at once. And then there's the plus A4, okay? And then I'm going to take a look at that little guy. And, that is also the union of three events. So I can apply my three-event formula, my three-event union formula, to that. It's just I got a lot more writing to do. Here it goes. So it's the sum. So I'm minusing off, because that was a minus here. I'm minusing off the sum of the three things that were getting unioned up, those three things probabilities together, minus the three ways of intersecting those things together. So this is one way, and this is another way, and this is a third way, plus the one way there is of intersecting all three of those doohickeys together. And so now all this stuff up here, I'm just going to call it stuff for short. And so here it is. And my intent is really to work with all the stuff that I'm subtracting off, okay? And so let's see, I've subtract off each of those three intersections, working the minus sign through. And then minus minus is pluses, so I've got some pluses coming up. And a minus plus here is a minus here. Now, I also took a look at all these complicated sets. So like A1 intersect A4, intersect A2, intersect A4, really it's just the same thing as an A1 intersect A2, intersect A4. And in the same way, I simplify each of these big intersections as much as I can by mentioning each individual set only once instead of multiple times. And that's how I get this stuff. And then I kind of group some things together, okay? And when I do all the grouping, I get the sum of these individual probabilities minus the probabilities for the 6 ways to take 2 out of the 4 sets and intersect them. That's all this stuff. And then there's 4 ways to take 3 of the 4 sets and intersect them. And I'm adding on those probabilities. And there's 1 way to take all 4 sets and intersect them. I'm subtracting off that probability. So that gives me the big complicated formula for the OR of 4 events. And these formulas for the OR of 2 events, 3 events, 4 events, they seem to be following a pattern that has stuff to do with combinations. Because it's got like all this number of ways to take, a couple of things out of a group and intersect those couple of things together. So actually, if you went ahead and did a formal proof with mathematical induction, if you took discrete math, you could actually handle this. You could prove general formula that the probability of the union of n events is the sum of their individual probabilities. Then you got to subtract off for all possible pairs of events the probability of the intersection of each pair. And so that would be n choose 2 terms there, because there's n choose 2 pairs of n things. And then there's going to be another n choose 3 terms that you've got to add in. And those are the probabilities of the intersection of each possible triple. And then you would minus off, and then you would plus on and minus off, and you would keep on going. And by the time you get to the final one, the pattern is a minus 1 to the n plus 1 of just one thing, the probability of the intersection of all n. So, great general formula. Now for the famous problem that I call the hats problem, okay? Suppose that n people, each one of them has their own hat. And the people are together somewhere in a room, and they throw their hats in the air, just kind of like way up in the air, and the hats kind of float around and fall back to the ground. And they scramble around and pick up hats. And each person randomly picks up a hat. So each person is equally likely to pick up any one of the n hats. In people, in hats, Each person equally likely to end up with each hat. What is the probability that at least one person picks up her own hat? Now, that probability is different for different values of n. But you would kind of imagine that if it's a lot of people, the chance of at least one person getting their own hat is probably pretty tiny. Suppose everybody in the world, which is 8 billion people. What if everybody got together and threw up their hat? And if you got your own hat, you'd be like, whoa, it's a 1 in 8 billion chance of that happening. God must be speaking to me somehow about something. But actually, the probability is not nearly as low as 1 in 8 billion, because it's not the probability that you get your own hat that I'm asking about. It's the probability that somebody gets their own hat. It's a bigger probability. But let's find out what it would be. So let's establish some notation here. For I, any number from 1 to n, let's let AI be the event that person I picks up his or her own hat. Then what we're really looking for is the probability of the union. Person 1 picks up their own hat, or person 2 picks up their own hat, blah, 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 all the way up to person n picks up their own hat. And we have a formula for that now. And the first part of that formula is where you sum up the probabilities of the AIs. So why don't we go ahead and just find the probability of A1, the probability the first person picks up her own hat. So what we can do here is we can imagine on the bottom of these little bar units is persons. And so you've got the task of assigning a hat to each person. They want to do it so that the event A1 occurs, which means that the hat belonging to person 1, I'll call it hat 1, has to go with person 1. But then after that, what are you going to assign to person 2? It could be any one of the n-1 remaining hats, and then person 3 could get any one of n-2 remaining hats, all the way down to person n only having 1 hat left that could be given to them. And so there's where person A1 gets their own hat. And of course, some of these other people could have got their own hat too. Doesn't matter. We're just getting the probability that A1 gets their own hat. And so we take that product there. So that would be a 1 here in the place of hat 1 times all those numbers. And that would be counting up the number of ways for the first person to get their own hat, the number of items in that event. And on the bottom here, I've got n factorial, which is the number of ways to just rearrange hats among people, n ways to the first person, n-1 to the second person, and so on. And because it's random how they went around and scrambled for hats, the equal likelihood principle applies. The number of things in the event divided by the number of things in the sample space gives us the probability. And so that comes down to n-1 factorial over n factorial. And so there's a lot of cancellation there, and you're left with an n on the bottom. So 1 over n is the probability for A1. Now it actually works. It's the same for the probability of A2 and probability of A3 and so on. In the analysis, where A2 is the person getting their own hat, hat 2 would have to go in that spot, and then you put an n-1 here, and then an n-2 and so on is the same. So you're still going to get a 1 over n. No matter which of those spots you relegate to only being filled in one way with the person's own hat. The other numbers are still the same, n-2 through a 1. So they're all going to be 1 over n's. And so that first part of the formula for the OR, where you sum up those probabilities, it's going to turn into n 1 over n's, which is a 1. Okay? So let's just mark that, put it to the side. The next thing in the formula is you subtract off the probability of all the intersections. So why don't we just find the probability of A1 intersect A2? Okay? So that means person 1 and person 2 each get their own hats. And so person 1 has to get a hat 1 here, and person 2 has to get a hat 2 here. So when I'm counting, that would be a 1, and that would be a 1 way. And then there's going to be n-2 and an n minus 3, and so on for the number of ways for the other people to get their own hats. Again, dividing by n factorial equal likelihood principal. We come to this. And I'm just going to leave that like it is for the moment. And I'm going to think. All the other probabilities, like A1 intersect A3's probability, and A1 intersect A4's probability, all the others, although the spots are going to be different, the numbers that go in the spots, they'll be the same, just in a different order. And so the top is still going to be an n minus 2 factorial, no matter what two sets you're intersecting. You're going to get this no matter what. And how many of these are there? Well, there were n choose 2 pairs of two sets, which works out to n times n minus 1 over 2 if you do the algebra for n choose 2. And so when you're adding up the probability for all those pairs, it's the n times n minus 1 over 2 times that answer you got for any one of the pairs. And lo and behold, there's a lot of cancellation, and you're only left with a half. So when you subtract off all those probabilities, you're going to be subtracting off a half. We start with a 1, we subtract off a half. Okay? That's what we got so far. And I'm going to deviously write that as 1 minus 1 over 2 factorial. And then you go ahead and do the kind of similar analysis to find the probability of A1 intersect A2 intersect A3. And it turns out to be this. And the probability is the same for all the triples. There's n choose 3 triples. Work out the math on n choose 3, and it turns out to be that. And so if you take all those probabilities, and there's this many of them, then the sum of all those together simplifies down a lot to 1 over 3 factorial. And you're supposed to add those on. So now we've got down to this. And continuing in this way, you would eventually find that the formula comes down to 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus and minus all the way to a plus negative 1 to the n plus 1 over n factorial. Now, I'm going to deviously rewrite that as this. That really does work, because 1 minus 1 is 0. And then this minus minus here becomes a plus, and this 1 over 1 factorial is the 1 that I was looking at here. And similarly, I got a minus this, like up here. And if I do a minus a plus negative 1 to the n, that's the same as that plus negative 1 to the n plus 1. So it's just a devious way of rewriting it. Now, suppose that so that's the exact answer. That is the exact answer to the HAPS problem. That's the probability that at least one person gets their own hat. But what if the number n was like really, really, really large? Then what I could do is just like, I could just like not stop that sum. See the sum here? Suppose I just like didn't stop it. So it went on like that forever. And so I could write it like that. Once you write it like that, that should remind you of the Maclaurin series for e to the x from Calc 2. And this is actually the Maclaurin series for e to the x, where you stick a negative 1 in for the x. So that infinite sum here is actually e to the negative 1. And so when there's a lot of people, the probability that at least one gets their own hat is this 1 here minus that infinite sum. That's what it's going to be close to. So the probability is going to be close to 1 minus 1 over e when n is big. And 1 over e is about 0.37, so 1 minus is at about 0.63. So that's like incredible. If everybody in the world threw up their own hat, there'd be about a 63% chance that at least one person would run around screaming that God had spoken to them by getting them their own hat back. Such is coincidence. it's often not as amazing as you might think it is. That's it for our section today. Hope you had fun. I certainly did. I'll see you around soon.